All right, this is page 382, question number 1. And we have this equation where N2O5 is going to be decomposed into 4NO2 and O2. The initial rate of reaction was determined by measuring the rate of change in the concentration of N2O5. And the temperature has to stay the same because if you change the temperature, it changes the rate. So we need to find the rate law equation for the reaction, and we're going to calculate the value of the rate constant. The generic equation is rate is equal to K, and then I'm going to write K, power of M, and B, the power of N. So this is for the equation A plus B yields products. The rate law equation does not involve the products at all.
So we don't care about the 4 and O2?
So we have 2 N2O5, that's all we care about.
Okay.
The 4 NO2 and the O2 we don't care about. This K is called the rate constant. And this whole equation is called the rate law equation. So this is what a rate law equation looks like. Let's fill it in. You only have one reactant, N2O5.
So
This counts as one reactant. We're not adding this to anything else. Like A was added to B, so that is going to be 2 reactants, A and B. N2O5 is just one reactant, and we don't know what the exponent is, and we're not going to say it's 2. It could be something else. Now, if we look at run number 1 and run number 2, we could use that. If we use run number 2 and run number 3, we could also use that. You could pick any of them to find your answer.
So it doesn't matter which one?
No, because it should be, you should get the same answer regardless of which runs you chose to determine your rate law equation.
But which one would you suggest? It doesn't matter. Which one?
I would not use run number 1. I would use the 0.190
And 0.275?
and 0.05. This is run 2. This is run 3.
Okay.
Initial concentration. The other column is initial rate. So this is how fast the reaction is happening. So I'm going to do it this way. 275 divided by 0.19,
Okay.
and that's going to be equal to a factor. So what factor is this number being multiplied to get this? Divided by 0.190. I want all the digits. So that's the factor between here and here. Now we're going to do the same thing for here. So this is the factor for the initial concentration. And now we're going to find the factor for the initial rate. Okay, it's almost the same. It's just like that. Factor of the initial concentration. So the power of some number
Is equal to the factor of the initial rate.
the rate.
This is where I use the logarithm.
Right.
Okay.
So it's probably going to be 1. You can tell, right? 1.44
Yeah.
to the power of 1 equals
It's gonna
1.44.
be
So that means M is 1. So you divide those two, and you should get 1, and that's what M is. So we're just going to use that formula over and over again to find this missing exponent. Question number 3. All we're going to do for number 3 is look at the data first, and oh, look at that equation. Not the products.
Yeah.
And this is the reactant.
And we have 2 reactors, right?
Right. So we're going to write. All right. So what is the rate law equation for this reaction? The rate law equation is going to be all of this. I'm going to finish, and I'm going to have an R equals. We have a number there with the units. So this is a value for K with the units. Then I'm going to have the I minus. I'm going to have a number here where the M is. And I'm going to have another number here where the N is. That's what a rate law equation should look like. You have to figure out which 2 trials to use. So I'm going to pick 2 where one of the reactants has the same initial concentration and the other reactant has a different initial concentration. I'm going to choose run number 1 and 2.
What do you mean by that?
12 is double 0.06. That's really hard to work with. I can't work with a factor of 0.5. It's kind of, I'm going to write it out again. What I'm going to do now is ignore this calculation and ignore this calculation. And I'm going to say, what do I have to multiply to get 0.06 to equal to 0.12? I'll multiply by 2. And this one is going to be times 1.
So you basically flipped it.
Yeah, I just like to have a whole number here. I don't want a decimal here.
Okay.
All right, so that means that I put the smaller numbers on top and the bigger numbers on the bottom. So I have 3.95. We don't need this anymore because it's the exact same thing as underneath. So I have 3.95 and 7.91. So in my head, what I'm doing is I'm saying 7.91 divided by 3.95. And what number should that be? That should be 2, roughly. It's 2.0025. That's close to 2. Okay, so that means this 3.95 times 2 will equal this, 7.91. My factors for the initial is going to be 2 to the power of m is equal to 2. See? And this is going to be m equals 1. So now I know m equals to 1. We're working on the rate law equation. This is the rate law equation. Piece by piece, I'm putting it together. I'm going to put a 1 here. Okay, let's try to find some data here where the initial concentration for iodide is constant from one trial to another, and the initial concentration for OCl changes. Nice. So this is going to be times 1, right?
Yeah.
So this time the iodide is constant, it's times 1, and the OCl is changing.
Yes.
So what number multiplied by 0.03 gives you 24?
8.
Yes. So this is times 8. Number times 9.88 will give me 7.91 times 10 to the negative 2. So the
8.
right, it's 8.
So it's the same thing as that one.
Right, which?
It's just going to be 1.
It's 1. So that means the n here is 1. Now we've got 2 of the numbers. There's only one number left to figure out this rate law equation, and that's k. We don't know what k is. You find one of these trials that has the nicest numbers, and I think trial number 1 has the nicest numbers because it's the smallest. Substitute all the values from run number into rate law equation. Now at this point I'm going to change and put the liters and the second on the bottom of the fraction. I'm going to put the same thing over here. So this is going to be liters to the power of 2 on the bottom. But when I move it, I'm not subtracting. This is a multiplication. How do you divide fractions? You have to flip the fraction upside down. This is L to the power of 2, 0.0216 mole to the power of 2. And that's equal to the K. Take 7.91 to the power of 10 to the negative 2 divided by 0.0216. I'm going to cancel out the L here and divide by 0.0216. And then I hit equal 3.66 liters, and then I put mole dot second. Proper number of significant digits is how many? How many significant digits?
2.
2, yes. So 3.7. All right, 3.7, 2 significant digits. We have the values, 3.7. The units is liters per mole second. Then you have your reactants, first reactants to the power of 1, and the second reactant to the power of 1.
I still need to do C.
So this is the whole point of doing this stuff, is to make a prediction of the future. If I have 0.15 moles per liter, I'm going to put it here.
And then just multiplies it.
Cancel out this one and this one with this one, and you're going to be left with, use 3.66, 203, 7037. use the same number that you had from before. Don't round it when you do these questions.
0.0823959.
Right. So 0.082. We have a mole of liter second. I always put dot s at the end. Sounds nicer. Okay, so that is how you figure out the rate, the initial rate for the investigation where both of them have that concentration. So you've never done this lab before, but if you start with these two concentrations, that's the rate that you're going to expect.